Hey guys, and welcome to another session. And in this session, we're going to be covering nodal analysis and some basic concepts again. So, yeah, so I decided that I'm going to be teaching you through the problems and not the concepts separately. So, in this session, we're going to be covering nodal analysis problems. So, by the end, you will be able to do this question, hopefully, that I have solved. That I've created for you. So, let's delve into it. So, this is an example I took from Sadiku. You can see, and the solutions, the answers are already given. So let's try to solve it. Okay, now the question is asking us to find some V1 and V2 and I1 I2 and power dissipated in 12 ohm and 40 ohm resistors. All right, now assume that I don't know any other method yet. All right, I know, for example, I know since I'm going to be teaching you all, so I know I must know nodal analysis, and there is series parallel analysis, and there is always sigma p equal to 0 also available to you. All right, don't forget about it. So you can, I think you should be able to think of these three particular methods whenever you start a question. Before starting a question, you should be able to think of these particular methods. And since I've not taught more nodal to you yet, assume that you don't know nodal. And let's solve this question through series parallel analysis. Okay. Now, so my rule number one always, as you know, is that whenever I see multiple points with a common potential, I instantly like to ground them. So this is 0, this is 0, this is 0. Right? Now, I'm asked to find, say, let's assume this as, you know what, let's assume this as V1, all right? This is V1 and this is 15 volts. As you rise through the voltage source, it becomes 15 volts. And this is V1, all right? All right. So, since I'm already given a V1, let's assume it as V. That would be better. That would be much better. All right. So as you can see in this figure that they have given us some particular V1, all right? And by logic, you can understand that V1 is equal to, since this it is decreasing here, V1 is equal to 15 minus V. I guess you can understand that, all right? Let's put it in a box. Okay. Now, that is my first equation also. Yeah. And now V2 similarly is equal to V minus 0, that is V2 is equal to V. This is my second equation. All right. Now, Uh, let's just try to solve it with a series parallel analysis. Okay. Now, since these two resistors are at common potential, that is V and 15. So these can be clubbed together into convert one R equivalent into the R equivalent. And similarly, these two also can be converted. So let's understand that. Okay, before actually writing numerical value of the R equivalent, let us understand what is going to happen exactly. So I know that for a fact that if I try to write the equivalent, if I try to combine these two resistors, then it's gonna create one R equivalent 1, right? And there is always the voltage source here that is not gonna change. And there is one R equivalent 2 here. And since this was in parallel, the potential is not gonna change regardless. So this will be still be, say this will be 15 volts and this is still V volts and this is still grounded. This is still 0 volts. This is still V1, this is still V2, right? So that's not going to change. Now let's actually calculate this numerical value of R equivalent 1. So R equivalent 1 is equal to 12 into 6 by 18 is equal to 4 ohms, right? And similarly, R equivalent 2 for me will be 40 into 10 by 50. That will be my 8 ohms. Yeah, 8 ohms. All right. So my equivalent resistance, my equivalent circuit will look like that. This is my 15 volts and this is my 4 ohms and this is my 8 ohms. All right. And this is my V1 and this is my V2. All right. Now you can easily calculate that V1 is equal to 15 by 4 plus 8 into 4. All right, and that will be my 15 by 3. Yeah, and that will be my 5 volts. And according to KCL and according to KVL, since if this voltage across this is 5 volts and voltage across the this will be 10 volts automatically, or you can also calculate this using 15 by 4 plus 8 into 8. So that will give me the values of V1 and V2, and that's there. This is a very straightforward question. So you got this. This is 5 volts and this is 10 volts. Right now, let's solve for some other things. Let's solve for some other things. Whatever is given. Let's see. Let's see. Now I know that V1, right? V1 is equal to what? My 15 minus V, and V1 is equal to 5 volts. So 5 is equal to 15 minus V, and V is equal to 10 volts. All right. Uh, I mean, if you there's no need for us to find actually, but still, like if you wanted to find, there's that. Now, I need to find this I1. What is this I1? This is my I1. Now, according to Ohm's law, I is equal to delta V by R. And this I1 will be my delta V is 15 minus V, or I already know that is V1 is equal to 5 volts, right? And my value of resistance is 12 ohm. So my answer will be, uh, yeah, it's already given here. My answer will be 106.7 milliamps. That will be my answer. All right. And now, similarly, I2 also you can calculate, that is delta V by R2, delta V2 by R2, let's say, whatever, you understood my point. Uh, that will be, they say the 10 volts divided by 40 ohms, that will be my 0.25 amps. That is 250 milliamps that's given in this particular answer. Now, the power P1 is equal to, P1 refers to this power, right? And power absorbed by this particular resistor will be delta V square by R. I'm going through this a little fast because I assume this is a very basic concept that you might already know. If you don't, just practice some of these problems and you will quickly get it in no time. So delta V1 square by R, that will be my 25 by R will be 12, and that will be my uh, like you calculate, that will be my 2.083 watts, and P2 will be this delta V, that is my 100 by 40 is equal to 2.5 watts, that is given here. So I assume you understood the question. So you'll get the fresh notes. This is a copy that I'm using in order to demonstrate the solving, because I promise that I'll solve in front of you guys. So you'll get the fresh notes. Don't worry about the notes. I've already have a copy of so the solve notes. Right. Now let's come to the famous nodal analysis. Okay. So let's, as I explained earlier, that we have to assume some voltages at particular levels at different nodes, and we have to calculate some parameters, whatever we have to calculate, we have to calculate those, and we have to solve that using the KCL, that is Kirchhoff's current law, that says that sigma I is equal to 0. As simple as that. So let's understand a question. Let's understand a question that we have to find some V1 and V2. That is this V1 and this V2. So generally, if there is some other parameter, say I had to find some I1 here. Okay, and if I've been asked to solve through nodal analysis, I would have to assume that this is V1, this has V2 anyways. So that's not going to be changed. That's not going to change in nodal analysis. But since they have already given me the this V1 and V2, so I have to assume these two as the names, for example, for it. Whereas otherwise, I would have taken this as V2 and this as V2 and this as V1. All right. But since the question is asking me to take these particular name convention, So I will use that. Okay. Now let's go at a particular node. Let's go at the node V1, right? Now the net current leaving is the net current entering. That is the visualization I'm going for. You can always go for the algebraic sum is zero. That is also in the end it's just maths. That is also possible. But I am gonna be using the net current leaving is equal to net current entering because I am comfortable with that approach. So let's apply the KCL at V1. Okay. Now the current leaving. Now so the assumption in this is very important. I would say that yeah, one assumption that we make assumption is that we assume that whatever voltage we are applying KCL for is higher, right? And now since we have gotten that out of the way, that assumption out of the way, let's understand this question, right? Now, since this is grounded, this is zero, and this is zero, this is zero, this is zero, this is zero, right? Now, net current leaving, let us understand at V1. So, one current that is leaving through here. So, how are we going to write that equation? If I, for example, I'm writing for this particular node, let's understand for V2, then I already know a current that is entering. I already know one current that is entering. So I don't need to write specific equations for that. I can just write 6 plus 12 is entering, right? I can simply write that. But what if I don't know the exact numerical value of current? You'll say, do just find it out, man. Like you know the resistance, you know the voltage drop across it. So like just find the resistance, just find the current, right? So what's the problem? And I'll say, yeah, you're pretty brilliant, man. You're pretty smart. Okay. And let's apply case here. So so for this particular thing, particular branch, my current, the value of current, the expression for current will be delta V, that is V1 minus 0 by 10. Now, similarly, for this one, it will be plus V1 minus 0 by 5 and plus V1 minus V2 by 2 and plus 12 amps because I know the exact numerical value of this particular current, right? And let's write the equation for V2. All right. And for V2, like I said, I already know the two particular currents that are entering it, right? So what I'm going to do is that again, the assumption is assumption says valid that for whatever node I'm writing the application, I mean, I'm writing the equation of KCL for, we are assuming it to be at higher polarity. So V2 minus V1 by 2, right? That is this current, okay? And and what other current is leaving? Yeah, plus V2 minus 0 by 4 is equal to 12 plus 6. Pretty straightforward. Now, when you solve these two, you get the equations as 2V1, 8V, my bad. The first equation will be 8V1 minus 5V2 is equal to minus 120. And second equation will be 3V2 minus 2V1 is equal to 72. Those are the two equations that you will get. And when you solve them, you simply input them in the calculator. You get the value of V1 is equal to 0 volts and V2 is equal to 24 volts. You can solve this on, I mean, you can just input it in the calculator. Just, simplify this particular expression, simplify this particular expression. And when you get in the format of these two, simply use your scientific calculator. There is a ax plus by plus e. You understood my point. So there's a format to find the answer for these two voltages. So I got the answer as 0 volts and 24 volts for this. And you don't have to, I have checked the answer through MATLAB. I have I tried it on Simulink and found out the answers. and they all match. So you don't need to worry about answers for this particular lecture at least. So I'll try if I can, use MATLAB and simulate and check the answers just in case for all the particular problems that I'm using. Let's see. Let's see what happens. But yeah, let's move on to the next question. So I'm asked to find I1, I2, I3, and I4. Okay. And since this is nodal analysis, I have to assume voltages now. So, okay. So, but the question is actually not specifying that whether this is you can do it by you have to do it by nodal analysis or any other analysis. But assume since the for this video that every question is saying that you have to solve through nodal analysis. Let's just assume. All right. Now let's get into it. Let's assume this as V1 and this also V1, this is V2, this is V2. Since why these are the same because there is no current element in between them. So the voltage is not going to change. So this is also V1 and this is also V2. That goes without saying. And let's just write equation, man. Let's just write equation. Let's see. We just write the KCL equation for V1 and V2. So let's write for V1. Now let's understand the theorem of KCL first. You know what? Let me explain the theorem of KCL to you. So what KCL exactly says is that the net current entering a particular node is the same as the net current leaving the particular node. Now it places no physical restraint on the particular what the node is supposed to be. So if you look at this particular question here, this is physically this may seem like these two are not the same. But from an electrical point of view, these two nodes are exactly the same because they are at constant potential. All right. So I can apply the, for example, for this particular, you may say that okay, so I will write the I'll write the expression for current for this. There is one current entering like this, and now you'll tell me what do I do about this? Now I'm just saying that ignore that and write the value of leaving current from here about this particular point because these two are electrically equivalent. The concept is electrically equivalent. No, an electrically equivalent nodes. All right. Now, okay. So what how you can think of is that since it is a particular region, the KCL says that you can apply KCL for any closed region. So if you are not able to understand this particular analogy, let's think of it in a different way. Think of that this is a closed region, right? So the net current leaving and net current entering in this particular region should also be zero because there is no new energy coming into the system. The system is receiving energy through this, through this, through this. But there is no another external energy that is coming when I'm writing this particular equation. Everything that is entering must also leave. Conservation of energy. All right. Any power supplied must be any energy supplied must be energy absorbed. All right. So I can write the value of I can write the expression for all the currents leaving the V1 and club them into one because they are the same node electrically. So let's write, let's write fine. So V1 by 5, V1 minus 0, let me ground this, right? V1 minus 0 by 5 plus, now let's write for this V1 minus 0 by 10. These are my leaving currents and my entering currents are 2 plus 4 amps. So this is my first equation, right? And let's write for V2. Now V2 minus 0 by 10 plus V2 minus 0 by 5 are my currents leaving plus 2 amps are my currents leaving and that is equal to my 5 amps that is entering. All right, so that is my equation 2. When you solve these two particular equations, you get something like you get some from this equation itself. You get V1 is equal to 20 volts and V2 is equal to 10 volts. All right. Now, once we have gotten these two, who is stopping us from finding the currents, right? So I1 would simply be V1 minus 0 by 5 is equal to your 20 by 5 is equal to 4 amps, and I2 will be V1 by 10 is equal to your 2 amps. I3 will be V2 by 10 is equal to 1 amps, and I4 will be V2 by 5 is equal to 2 amps. Okay, now let's let's actually check whether this is true or not. Okay, so it said that the 5 amps, the question says that 5 amps is entering here, and I4 is this particular current is my 2 amps. So technically, there should, but that goes without saying, I should say that 3 amps is entering here, 3 amps is leaving through this particular point. So that means that 3 amps is entering here and 2 amps is leaving from here. So that means that if 3 amps is entering and 2 amps is leaving, then 1 amp must also leave in order to maintain the KCL. And you can see that I3 is 1 amp. So that means that KCL is valid. Is right. It came out right. So by this particular approach. So it means that these are electrically equivalent nodes. So from next time, do not go for any other analogy to make your life easier. Just consider the same as them as the same, and write the equation for V1 as considering them the same. All right. Let's move on to the next question. So I'm going to be teaching you dependent sources as well, because what I believe is that there is nothing new in dependent source. It is just an extra equation that you have to take into, and you guys are not solving it, right? You guys are not solving manually. Anyways, you're inputting it in the calculator. So what is this? One more equation for you guys. So dependent sources are very easy, and as per a basics of electrical engineering point of view. So they are very easy. I mean, I don't get the why I don't get why people call it so difficult, but yeah, fine. So I have to find, the question says that I have to find I naught in the circuit. That is my this I naught. Now, as you can see that there's something, okay, you don't know what it is, say, for example, you don't know what it is, and you are trying to guess what it is. You saw this particular symbol, right? You saw this arrow, and you said, oh my, this must be a current source. So let me check the value of current, and it is saying something like 2 I naught. So you must have understood that the value of the current in this particular branch depends on some other current. So this is something called a current controlled current source. All right. All right. Now let's try to solve this. Fine. Let me ground this. This will be my 0. This is 0, and this is 0. Now since we are solving by nodal analysis, let's assume voltages V1 here, V2 here, and V3 here. Right, pretty straightforward. Now let's try writing the KCL equations for all these nodes. Let's start from V1. So I already know one current that is leaving, the numerical value of the current. So I don't need to write an expression for this. I need an expression for this. I need an expression for this. Okay. So let's write the expression. V1 minus V3 by 1, that is delta V by R, is my current that is leaving through here. and V1 minus 0 by 8 is my current leaving through here, plus V1 minus 0 by 8, that is my current leaving. And one more current, the numerical value of current is given to me, that is 4 amps. So that should be 0. Okay. And and you should go ahead and solve this one and simplify this one, and you'll get one equation. Okay. Now let's solve for V2. Now again, I know I know a value, the numerical value of this particular current, that is 2I naught. But sadly, I don't know the numerical value of I naught. But I already have an equation that what is exactly I naught. Let's understand what is this I naught. Whenever you have a current, whenever you have a dependent source, and there is some particular equation, there is some gain. This is your gain basically, and this is your parameter, the varying parameter. So instantly write the equation for that particular parameter. So what is my I naught exactly? The I naught is simply your this thing V1 minus 0 by 8. That is V1 by 8, right? So that completely changes everything, right? That you don't have to worry about it being a dependent source, whatever. You have another equation with you. So so you know that one current that the current that is leaving is 2 I naught. So let me just write 2 I naught. That is 2 into V1 by 8. That is one of my current leaving. Now again V2 by 2, and one the current that is entering is 4 amps. So this will become my 4, and you'll get another equation by this, equation number 2. So this call this equation number 1 and call this equation number 2, and you solve this basically. And let's write for V3 now. Now V3 minus V1 by 1 plus V3 minus 0 by 4. Now one current is entering again, that is 2 I naught. So I know the particular equation for it, that is I naught is equal to V1 by 8, and 2 I naught is equal to V1 by 4. So you got three equations here. You put them in the calculator, you get the answer as you get the answer of I naught is equal to minus 4 amps. Your V1, if you want to match the answers, V1 is equal to minus 32 volts, V2 is equal to 24 volts, and V1 equal to V3 basically, and V3 becomes your minus 32 volts. I verified this through MATLAB, but still, if you face any problems, if you feel that my answer is wrong, you understood the method basically. That's all that matters, right? Don't worry about the answer. Even if your answer is wrong, especially in electrical, there may be cases where you may make a you make a silly mistake. But if your explanation is right, as long as your explanation is right, you will get partial marks. You don't need to worry about that. So focus on the concept more than the answer. Having the correct answer is very important because you have to minimize the silly errors as much as possible. That is very true. But don't get so caught up in finding the answer that you forget the concept. Okay. Now let's understand the next question. I have to find this V naught in the circuit and to nodal analysis, obviously. Now let's this is all they have already grounded it for me, thank god. Okay, so they've already grounded it for me. This is my 0 and this is my 0, this is my 0, this is my 0, this is my 0. All right, and since it's nodal analysis, I'll assume voltages. This is V1 and this is V2. Okay, and I have to find out V naught. Now if by KVL or what means through simple analysis, through nodal analysis, you can say that this is 30 volts. Voltage is rising by 30 volts. Okay, now let's write the equation, KCL equation for everything. Now V1, okay, now V1 equation for this particular current that is leaving would be V1 minus 30 by 10 ohms, right, plus V1 minus V2 by 1, that is another current leaving, plus V1 by 2, is equal to 0. So these are the net currently and leaving is 0. Okay. Now solve this particular equation and I mean simplify this particular equation. Now let's write for V2. So V2 minus V1 by 1 plus V2 minus 0 by 5 plus. Uh, so this is my current that is entering. So as you can see from the previous, even from the previous problem, you can understand that this is a current controlled current source. That is, this is my gain and this is my parameter. So the value of this particular current depends on some other particular current. This Ix, let's identify this Ix. This is my Ix. So again, there is just one more equation. Ix is simply V1 minus 0 by 2, that is V1 by 2. Alright. Now, once we have gotten that out of the way, we can simply write 4 into Ix is equal to 2V1. So I'll just write it as 2V1 here. So this is my equation 1, this is my equation 2. So two equations, two variables. So you'll get the answer as uh, you get V1 is equal to minus 3.33 volts, V2 is equal to minus 8.33 volts. And what we had to find in this particular question was our V naught. But you can clearly understand that V naught is simply V2. V2 minus 0 is equal to V naught. So I'll just write the answer as V naught is equal to V2 is equal to minus 8.33 volts. Pretty straightforward. Okay. If you face if I have made any mistake over writing the equation here, you don't have to worry about it. If you just have to understand the concept and just check my notes. Basically, my notes answer matches with the MATLAB simulation. I mean the equations match with the answer at least. So answer matches. So the equations must be right. So yeah, let's focus on the concept here. Right. Now let me take this color. Yeah. Again, I have to find some I naught, and this is my I naught. Okay, and the power dissipated in each resistor. Okay, now do you understand this though? What is this particular symbol? What is this particular units? These are Simon. Simon is the unit of conductance, and you guys already know that conductance G is equal to 1 by R. So essentially, if I say that I have been given a conductance of 5 Simon, it implies that I'm given a zero point 0.2 ohm resistor. It's as simple as that. All right. So you know why in nodal analysis especially, it is sometimes very good to convert things into conductances. I'll tell you why. Because when you are writing V1 minus V3 by the R, it is, I mean, you have to cross multiply and you have to simplify that stuff, right? So instead of that, if I had already calculated the particular conductance, then I could just simply multiply that V1 minus V3 into the conductance G plus V3 minus V4 into some conductance G2. You get my point. So sometimes it is better to convert into the conductances, but even if you don't, it's fine. You can understand. I mean, in the end, it's just a reciprocal. You can just cross multiply. Okay, let's solve this particular question. Now, I'll make this a 0. Okay, and I'll assume this as V1. Okay, and this is my V2 and this is my V3. Now, I will introduce a concept called a supernode. All right. Now, I'll show you why I introduced that. I mean, you already might have understood from your classes why you are using the supernode, but still, if you're new to this, let me understood. Let me make you understand that why I am introducing this particular concept called supernode. Okay. Now, let us, you know what, you know what, let's write the equations. Let's just write the equations. V1, V1 minus 0 by 1 by 6, or you understand my point that you can simply write them as a multiplication factor. That's 6 Simon into V1 minus 0. That is my current leaving. Okay, and I know that another current leaving is simply 2 amps. All right, now I'm stuck trying to find this particular thing. What is the current in this particular branch? So that's why you need something called a supernode. Now the statement of KCL that the net current, that's the algebraic sum of the current entering or leaving into the in a particular closed region is zero, comes into a lot of use here. Now I can consider this particular thing, this particular region as a closed system. And for this particular closed system, I can still apply the sigma I is equal to zero. It is still valid because the theorem literally states that it should just be a closed area, closed region. Now, but if I okay, but what I'm trying to say, let me show you numerically what I'm trying to say is that you get you apply you can you're since you're considering them both as the same net as the same closed region. So I will just write it. I'll just write the another current that is leaving for with respect to V2. Now, what about you'll ask me what happened to the there will be some current here, there will be some current here, right? And I will say, okay, you know what? Let me just I'll come to that. I'll come to that. Okay. Let me write the current exiting V2. Now, the current exiting V2 would be V2 minus V3 into 3 Simons plus V2 minus 0 into 5 Simons. These are my currents leaving V2. Now, Anish, what about the internal current? The current that was going here or the current that was entering here, whatever. There would have been some current, right? And I'm saying just treat it as an internal current concept, internal current. It is bound to get cancelled. See, I'll explain you how. This is visualization one. This is quite fast. You can just ignore the internal current. But if you want to understand where is this coming from, visualization one, you have to go through visualization two in order to understand the first one. You know what? In order to understand visualization two, I'll just simply show you the algebra. Simply show you the algebra. What you are saying is that for this particular region, some current, say I1, I1 was leaving this particular node and it was entering V2. And if that is the case, then minus I, okay, now there are further different ways to see this. Okay, let uh, let me make you understand in this way. Since I1 current is going through here, that implies that minus I1 was entering here. I mean that I1 was entering here. My bad. I1 was entering here. If I1 was leaving V1, then it implies that I1 was entering V2. So what I'm trying to say is that simply write I1 here also. That it is the current entering this region. This current is leaving the region and this current is entering the region. So they are getting cancelled. So that's what I meant by internal current. You can simply neglect the internal current. Now, but Anish, I don't know what V2 is exactly. What is this V2? And I'll say that come on, it's smarter than this. V2 is simply V1 minus 10. Alright. Now, this is one of my equations. So this is, if you cancel these two, this will be one of my equations, say this, let's call this equation 2, and this is my equation 1. So I have v3 as the variable, v2 as the variable, and v1 as the variable, and I have two equations to solve these two. So I need one more. So let's go for v3 here. Now, once you have understood the supernode concept, then you it's very easy to apply for one particular node, right? You don't have to, you're not, this is not some super node, you're just simply applying for v3 here. Now, the current leaving v3 is simply v3 minus v2 into 3 Simons, and the current entering is 2 plus 4. This is my equation number 3. Three equations and three variables. So if you simplify and solve these, the answer you will get is that your I naught, I had to find this particular I naught. Your I naught is 29.454 amps. Right? So that is my value of I naught. Now you try solving for the power. I won't solve for the power because you have all the delta V here. You have all the potential differences. You have all the conductances here. Convert them back to uh, resistance by 1 by R and V square by R, or simply apply a little logic and say that if power is equal to delta V square by R, then it implies that power is equal to delta V square into G. So this will make your life easier. Okay, so let's move on. Let's move on. Everything is pretty straightforward. It's just maths. It's just a little inside concept that you have to think. What is happening internally? All right. Now let's see this particular question. It is asking me to find V1 and V3 in this particular circuit. Okay, this is my V2. This is my 2 V naught. This is my 13 volts. This is my 2 amps. Everything is given. All right. Now my classic approach is grounding 0, 0, 0, 0. V1, I'm already given V1, we have V2 and V3 here. So let me just start writing in the equations, all right? So V1, so for V1, V1 minus V3 into 2 Simons, that is my current, one of my current leaving, and plus V1 minus 0 into 1 Simon, that is another one of my currents leaving. And since you can already see, you might have already guessed that this is a supernode here. So this is define this for you. Let me define this for you. This is something called a voltage controlled voltage source. Right? This is a voltage controlled voltage source. Okay. Now it is saying that the potential drop across these 2 points is something called 2 V naught. And so the what is let's find out what this V naught is exactly. And you can instantly spot this particular V naught here. So you can instantly say that my V naught is equal to V2 minus 0. My V naught is equal to V2. As simple as that. My V naught is equal to V2. V2 is equal to V1 minus 2 V naught. V2 is equal to V1 minus 2 V2, and V1 is equal to 3 V2. One equation. Okay. Now let's write again for this particular thing. Let's write this particular thing again. The supernode, the equation for supernode. Now let's continue this. Let me write it again. V1 minus V3 into 2 Simons plus V1 into 1 Simon. Okay. Now let's write for V2 side plus V2 minus 0 into 4 Simon. Okay. And another current now of V2 minus V3 into 8 Simon is equal to 0. And this is my equation 2. Okay. And one final, I have two equation and three variables. So I need one last equation, and let's apply at V3. V3 minus V1 by, my bad. V3 minus V1 into 2 Simon plus, okay. I don't actually need to find out if the V3, I'm already given the V3. My V3 is simply 13 volts. So it's not a three variable, three equations question. It's a two variable, two equation question. You can simply substitute V3 here with 13 volts, V3 here with 13 volts and solve, and you will get your answer will be V1 is equal to 12 volts and V2 is equal to 8 volts. Solve this. Okay. Now let's move on to the next one. Okay. So I have to find the V1, V2, V3 using nodal analysis. Okay. Now, uh, let's start with the grounding. This is grounded, this is 0, this is 0, this is 0. Okay. Let's start with V1. Now, V1 by 4. So this is not conductance, this is resistance. You have to be very careful about this. V1 by 4 is one current leaving. Now, let me mark this as a very good question. I've already marked this in your notes. Good question. Why? Because it this question helps you understand what kind of closed region are you allowed to assume. Now, you can see that this is a supernode, but you can also see that this is also my supernode. Hmm. Now, what to do? You can either consider that this is my one supernode, and then it will simply be, see, if in the end everything is just linear equations. Everything we have done so far is just linear equations, right? If you're not interested in finding if you don't want to complicate stuff, you can simply write v3 is equal to v1 minus 12. That is one of your equation. And then v2 is equal to v1 minus 2i. Okay. And let's understand this I as a parameter. I is equal to v3 by 4. So my V2 is equal to V1 minus V3 by 2. This is my second equation. And simply apply, at a particular point, say, let's say simply applied V3, then you need to assume one supernode at least. You need to assume one supernode at least to get a particular equation. So let me still try to think of some other way if there is any possible way. Uh, okay. Hmm, hmm. Now you have to assume one supernode. Say I'm considering this particular closed region. So let me write the equation v1 uh, v1 by 4 plus so let's say mm, hmm, okay, let me come back if I'm not getting this particular approach. Okay, so what I will go by I will go by the method that I can think of right now. There is another method. There are so many methods that are much easier than this, but right now this is only striking to me. What I'm gonna do is I'm gonna assume this entire thing as a supernode. Okay. Why am I trying to do that? Is because I can write the equation of KCL for this entire particular region. Okay. And let me just check in why, just in case if I can, maybe simplify this more. Because in the end you have to understand it, right? I'm trying to make it as simplified as possible, but it appears that I can only think of this particular method right now. So let me just think of something. You can skip, you can forward this video. I mean, uh, hmm, okay. So if I'm assuming, if I'm writing the equation here, then say this one is one of my current living, current living, and my current is entering here. Mm, if I write for here, then okay, fine. We have to assume one supernode at least. Okay, so let's write for V3. Okay, let me make it as simplified as possible. Let me write it for V3 here. Why I have taken V3 here exactly is because I don't have to deal with two two dependent, I mean two sources at once, two supernodes at once. How is that if I consider this as one particular supernode, uh, nah, okay, you have to consider this everything entire thing as a supernode. Hmm. Okay, no problem, no problem. It's in the end, it's just algebra, so you don't need to make it much complicated. Fine. So what you can do about this is that you consider this entire thing as a supernode. Okay, and now write the net current entering is equal to net current leaving equation. Okay, so V3 for let's write from V1 side. Let's write from V1 side. Let's write from the V1 side. Now V1 by 4. Okay, that is one of my current leaving. Okay, and let's go if I'm like everything is internal current, everything in the supernode. The good thing about a supernode is the internal current concept that I taught you. So everything is going to get cancelled in between these two. That's why I was thinking to solve by a supernode by taking the supernode, but I tried to think of another method that can maybe make it less make it more simplified, but at least for right now I can't think of one. Okay, so this is my internal current. You can either do the algebra and cancel them, or you can simply treat them as internal current and not write them. So there is one current that is entering from into V3 from V1, and so that is going to be one side and is equal to some I is equal to I. So this is going to also get cancelled. Okay, so V1 by 4 is the current that is leaving here. V2 by 1 plus V2 by 1 is one current, that is another current that is leaving. Now again, V plus V3 by 4 is another current that's leaving. Now, you can either treat this also as an internal current. If you're finding this question really hard, you can skip. This is a little a little hard. I mean, no, this is a good question. I won't call it hard. This requires a little bit algebra, either algebra or good visualization. I am trying to solve it by internal current concept. That is my visualization that I've developed through algebra. But if it's like a little bit above your capabilities right now, you can skip this question and go to the next one. But if you want to understand, this is a very good question to understand. This is gonna help you build your concepts a lot. Okay. Now, see, you can either write. Okay, if you don't want to cancel this current, you're confused at what currents am I supposed to cancel, what current am I supposed to include. Simply do the algebra. Algebra will take care of everything. Say, for example, if I'm confused whether this is my internal current or not, let me just write the equation. Say V2 minus V3 by 2 is my current leaving. Similarly, V3 minus V2 by 2 is my current leaving. Now, current I'm entering will be V3 minus V2 by 2 plus V2 minus V3 by 2. So this is going to cancel, this is going to cancel, this is going to cancel. So in the end, I'm going to be left with this particular equation. So I have three equations, three unknowns. Now you solve these and you get the answer as V1 is equal to minus 3 volts, V2 is equal to 4.5 volts, and V3 is equal to minus 15 volts. I'm covering the like hardest possible questions possible. I mean hardest possible questions. So this is going to be a very good practice for you if you're feeling confident in your by solving your normal problems. You can come to these problems. Okay. Now let us understand this particular question. How many questions are left? Yeah, only two questions, and the one in the beginning. That's a good question, and that's a good question that I'll come back to that. I'll come back to that. Don't worry. Okay. So yeah, I have to determine V1 and V2. Okay. Now, as usual, this is my ground, this is my zero, this is my zero, this is my zero. This will be my minus 5 V naught. So instantly I will write the parameter V naught is equal to your, since this is my zero, this is my 12 volts. And as you can see in the picture that V naught is equal to 12 minus V1. That is my equation number one. Okay. Now simply write nodal analysis equation, that is the KCL equation for V1 and V2. Now for V1, the one current that is leaving will be V1 minus 12 by 2 plus V1 minus 0 by 4 plus V1 minus V2 by 8 plus 3 amps is leaving. Simplify it. Let's write for V2. For V2, V2 minus V1 by 8 plus okay, this is my another current that is leaving. V2 minus of minus 5 V naught by 1. Okay, that is my another current and is equal to 3 amps current that is entering. All right. Now simplify. You can simply input this V naught here. So it ultimately it's a question of uh, two variables and two equation. Solve these two. Put them in a calculator. Solve these two. You'll get the answers of V1 and V2 as V1. Yeah. So answer will be V1 is equal to minus 10.909 volts and V2 is equal to minus 100.363 volts, right? And V2, and if you want to find out V naught, your V naught will be simply the 12 minus V1. So it appears that I think I haven't calculated. You can say you can calculate it. So you will get that as your answer if your V2 is V naught is required. Okay. Now let's go to the second last question. Now again, uh, this I have tried using MATLAB and the answer was confirmed. I confirmed the answer. Now let's instantly ground this without any thinking. Without even reading the question, let me just ground this. Makes my life easier. And it's saying nodal analysis. So I'll quickly assume voltages. This is my V1. This is my V2. All right. Okay. Wait. Let me go chronologically. So this is my V1. This is my V2, and this is my V3. So since this is V3, this will also be V3. If this is V3, this will also be V3, and this will also be V3. So essentially, these two are electrically equivalent nodes. And since they are electrically equivalent nodes, then any current, if I'm, for example, if I'm writing for V3, the concept here, why I took this particular question is internal current or current between electrically equivalent nodes is gets cancelled, either gets cancelled is or is neglected. That's the concept here. So uh, let me directly come to the point. Let me try to understand. Let me try to make you understand V3, right? Since this question is good to in order to understand the concept of V3. Give me a second. Yeah, all right. Now let's write the equation of KCL for V3. Now V3 minus V2 by 4. That will be my this current, and V3 minus V1 by 8 plus V3 minus V1 by 8. Okay, that will be my another current. That will be my this current. Okay, and I need essentially which current do I need? Okay, I have more currents actually to deal with. I have something called V3 minus 0 by 1 and V3 minus 0 by 2 as two other currents that are leaving. Okay. Now, what I'm trying to explain you is that if you want to consider this, if you say that I don't understand this concept of internal current or current between electrical equivalent nodes, like I've always been saying, simply do the algebra. According to V3, 2 amps is leaving, right? And equal to the current entering. So the current entering is inside V3 only. The 2 amps considered and the current is entering in V3 only. So write 2 here also and cancel these two. That makes your life a lot easier, right? I mean, if you are struggling with this, if you're struggling with this concept, then simply do the algebra. But it would be good. I mean, it would be much better if you could, because it makes your calculations quicker, right? You don't need to do the algebra and cancel these two. You can instantly understand, and that gives you a sense of satisfaction and confidence also, I would say. Okay. Now, this is one of my equations. And then for like right for V1, then V1 minus V3 by 8 plus V1 minus 0 by 1 plus say, so my 4 amp current is entering is equal to 4. That will be my equation number 2. And for right for equation number for V2, so V2 minus 0 by 2 plus V2 minus V3 by 4, that this current, and this is also leaving. So add 4 here is equal to 0. This is my equation number 3. Okay. So uh yeah, I think I solved it. Yeah, yeah. So you get the answer as, you get V1 is equal to 3.5 volts, V2 is equal to minus 5.5 volts, V3 is equal to minus zero point 0.5 volts. And since let's understand this V naught, okay? So the question is essentially asking us to find something called V naught. So as you can understand it, V naught is equal to V1 minus V3. So simply do 3.5 minus of minus zero point 0.5, you will get as 4 volts as the answer. This is my answer to the question. Okay, so these are all very good concepts that conceptual examples that I picked from the from the textbook. I hope you guys like these examples. Let's end it on this particular question. Now, I'm expecting you to pause before every question and trying it yourself, but try it especially for this question. Pause this question for 5 minutes and try to solve whatever I have marked these parameters, right? Try to find these 4 parameters and tell me what do you think the answer is. Okay, I'm assuming you guys would have tried it by now and would have failed miserably because the I'll tell you what I was trying to do. That I initially made this question and I solved it and I didn't find anything suspicious. Now, a couple of days before, I was trying to solve it again, just in case, to make sure the answers were correct. And I found out that I had made a very big mistake. Okay, let me show you what. Okay, my thought process is always ground. I mean, let me do in this particular figure that I've created specifically for solving. So this is my zero. Now, since there is no particular current element here, so this will also be zero, and this will also be zero. All right. So you will say that this is zero and this is zero. Haha, you will say that since this is 0, this is 0, your I3 is equal to 0 amps, because or else there would have been some potential difference, right? But if there is no potential difference and there is a resistor in between, then it implies that the current is by default 0 amps. Okay, good. Now now you'll go to this particular I1, right? You will go and you'll say, okay, I1 is simply say for example, if this is my 0, uh, if this is my 0, then this is my 0 and this is my 0. So haha, your I3 also 0. You'll say that my I2 is also equal to 0. Okay, and then you'll say that since this is 0, then this is 3 volts, this is 5 volts, and I1 is equal to 5 minus 0 by 6 ohm. Then you will report me this as the answer. And since this is 0, this is 5, your this thing, the value of power here, you will since the power here was asked to you, the power will be uh, 5 minus 0 by 8 into wait, let me find out the current. So this is my current, right? Delta delta V by R is my current here, and I square into 4, you will report this as the answer to me, and you'll say that I have solved the question. This nodal analysis was very easy. And I tell you that you made the exactly same mistake that I made. You want to know the answer for this particular question? It's not like I did this on purpose, okay? It's not like I created this question on purpose. Even uh, I confused the answer. I mean, I did not think this through. I reported these as the answer. I wrote these as the answer for the first attempt. Now, I'll tell you what the problem with this particular approach is. You completely neglected this particular voltage source. Now, if the answer, if you're asking me the answer, you have to answer as that the answer for this particular question is that question is invalid. Question is invalid because you did not consider this particular voltage source at all. Okay. Now, what is going to happen? What I'm trying to say is that a voltage source has to maintain a constant potential difference across for 4 volts across it. But since I've grounded this physically, the network is trying to maintain 0 volt here and 0 volt here. But so it's like two stubborn people fighting. None is ready to compromise. This is saying that it has to be 0 volts. I will not change. And this is also arguing that I will be 4 volts. So if you want a numerical answer, the numerical answer is question is invalid. But if you want to understand physically what is going to happen is that apparently the wire this is going to get damaged and wire is going to melt. Let us understand why. Now this is a very beautiful question. I would say this is a very beautiful question. A question that I did not do it intentionally. I'm not taking credit for it. I didn't do it intentionally. It just happened. So it's a very good learning opportunity for you, for me as well. Yeah. I had to, understand this, what is happening to it physically. Even I did not know what is going to happen to it physically. So, let's understand this. So, this the voltage source maintains constant potential difference of 4 volt by changing the current. Varies. This varies. It changes the particular current to match this particular voltage, right? And this is since the potential difference is 0 volt and it is trying to convert it to 4 volts, it is going to increase the current in its particular branch. Why? Because V is equal to IR. Delta V is equal to IR. So in order to make it 4 volts, in order to increase it, it will try to, since this is constant, it will try to increase the I. But essentially speaking, this is R is, is close to 0, R tends to 0, right? Uh, Essentially speaking. But the voltage source doesn't understand it apparently. It tries to keep on increasing the current, increasing the current, increasing the current till a particular point that I tends to infinity. No matter what happens, the in the end you see it's like two strong people, two buffed up people are fighting, and you're asking me who wins. In the end, this one, because no matter how hard it tried, it increased the current to infinity, but still it could not achieve what it wanted to achieve. So this is going to get damaged. The wires are gonna melt, and essentially this becomes an open circuit. Basically, you just remove this particular part and solve. If you want to solve, then solve using this. Then if you solve, then you'll get the answer as right. Yeah, this is since the our previous answer as right, because we didn't consider this voltage source then, so your answer will be right then. But if I give you this question and I ask you the answer, you have to report to me that the question is invalid. So I hope you appreciated the beauty of the question, beauty of an invalid question, I must say. And let's end it here. This is a 1 hour 10 minutes video. I just watch it on. I am speaking really fast, so I don't think you'll be able to watch it at 2x speed or something. But just try, man. No, not I mean not watching it at 2x speed. Just try solving it because everything is simply concept, and just go at your own pace. You may not understand the things right now, by after consecutive exams, after you try the problem again and again, by the end, I'm pretty sure that you will be able to understand it. Okay, no matter the concept, even three-phase systems, people find three-phase systems hard because it is introduced at the end, so you don't have enough practice for it. But for concept such as this nodal and mesh, you are constantly studying it again and again for mid-sem, for minus mid-sem and end-sem. So it's like a second nature to you. So that's why I guess people are so comfortable with nodal and mesh, but some not with some other concepts. But again, like I said, that keep on practicing it again, and by the end, because everything is end sems, right? So you get what 50% is through your end sem. So by the end sem, at least you will be able to have a good hold over this. And let's end this video. Thank you for watching, and I'll see you in the next video where I'll be covering mesh analysis. Thank you.